Walter country fellow.
Please remind us when I get a stock. Something.
Sorry?
Please remind us that I offer myself when I got the stock or mistakes in the slides.
So Walter, for those who don't know, Walter is a postdoc at ICTP-SAIFR and IFT. And he did his PhD at the IFT, but not this IFT, the wrong IFT, the IFT Madrid. So in Madrid, they have Instituto de Física Teórica also. They call it IFT. But ours is younger. No, better and was before. So they should pay royalties.
Right.
That's I have to discuss it before. And after this, so Walter is an expert in primordial non-Gaussianities in galaxy distributions, in two-point functions. So we work on this in DS. He's in charge, now he's responsible for the, that's a big, he's responsible for the final year 6 dark energy survey analysis of primordial non-Gaussianities in two-point functions. And he's also working in LSST. And on his free time, he also works on gravitational waves. And so we've Ricardo Bravo, Roberto Bravo, Rafael Bravo.
Close enough.
Eventually I would get it right. With Rafael Bravo, he had a work on imprints of large-scale structure and the cosmological gravitational wave background. So please go ahead.
Okay. So hello everyone. As Rogero mentioned, this is something like a side project to me. So I'm basically not an expert in gravitational waves. I do know some things about gravitational waves, but mostly from the cosmological perspective. And during this talk, I will be referring to some well-known things from astrophysical gravitational waves. So I'm hoping that maybe the people that is an expert in gravitational waves can help me with something that I might say wrong.
So Studani will not be here.
Well, become a student.
I am.
Ah, you are. Oh, you're a voice from the heavens. All right. Okay, so today is virtually here.
Right. So here's the one that
What?
What you said, Riquelme?
I'm watching you.
Now I feel the pressure now. Well, that's some students, so I think they're gonna help. So the idea of this work is it started as a side project because I was mostly interested on LSS. My friend Rafael Bravo, he's interested in gravitational waves, so we are friends from years, and we say, okay, let's start to do something together. And this idea started to grow from the summer up until now. And the title of the talk is Imprints of LSS on the Cosmological Gravitational Wave Background. So I have one slide referring of what is the stochastic gravitational wave background. And the idea behind it is that it's basically a gravitational wave signal that spans like a frequency range and is particularly not localized in particular regions of the sky. And this signal, the interesting part of this signal is it can be produced for different procedures. So for example, here in the early universe, you can produce this stochastic gravitational background by a period of inflation, so some certain mechanism during the inflation era. Then you can have also some effect in the gravitational waves due to phase transitions. And also you can be like more of the usual gravitational wave analysis is by, you can produce this stochastic background to considering gravitational wave produced by bigger objects or black holes or neutron stars or things like that. So it has different sources. And the interesting part of this stochastic gravitational wave background is that the PTA collaboration actually announced a detection of this stochastic gravitational wave background. The idea of how they do this with pulsar timing arrays is that they have a collection of pulsars, and then they can try to measure time shifts in the emitted light that arrives to us in Earth. And these time shifts is supposedly to be produced by gravitational waves passing through the pulsars. And by using this time shift, they can try to measure the gravitational waves. And the interesting thing is that here in this plot, you can see in gray the signal detected by nanogram, and in different colors, for example, in these yellow things, you can have the signal from supermassive black hole binaries producing these stochastic gravitational wave background. And then here you have a series of cosmological models that could produce this same signal. So in principle, there is no agreement on what is the source of this signal here. It could be either astrophysical, that is coming from supermassive black holes, or it could be cosmological, or with whatever of these models could work.
Sorry, I'm confused. So the signal is the time delay.
Yes.
The pulsar,
Yes.
the pulsar, the like things. And then, but then in this plot, you have a contribution to omega gravitational waves. So
Right.
how
So
does that translate?
that is the details, and I'm not really sure. But they are able to measure, for example, the correlation in the time delays of these pulsars, and these relate somehow to the gravitational wave density. But I'm not sure in the details how they connect the time delay shift correlations with the omega gravitational waves.
Because the way, so naively, I would think that the gravitational wave contribution to omega is a background contribution. So kind of homogeneous, more or less. But this is not the case.
Yes, this is the case. This is the stochastic gravitational wave background, right? It's a homogeneous
This is homogeneous.
background of gravitational waves.
But there are correlations, no?
There are correlations in the at the time of how they measure it. There are correlations in the signals of the pulses. So they use correlations in these time shifts to check for the gravitational waves. But the gravitational waves up to this point is just homogeneous. So background without isotropies or anything.
So basically, they from the frequency they infer a strain on a Bayesian probabilistic model. Like if I measure the signal on this frequency, there should be this energy associated, this strain associated, and that's how integrating over the whole volume they get homology down. Now the frequency is measured in terms of correlations between noise amongst the various pulses. So when they see some coherent noise amongst all of them, they convert it into frequency, and that's why the error bars are huge.
Yes.
And from that, they infer density of power emitted by this coherent
Right.
frequency.
So they have to integrate over all frequencies to get omega.
to get omega GW.
But then for each frequency, they have an omega GW.
That's the contribution of that frequency to omega GW.
So integrating a band.
Yes, precisely.
I think that we have an expert.
Not really. It was an interesting.
Ricardo.
So the
Yes.
claim is that they have detected. Ricardo has a
Yeah,
question.
shall I? No, what is crucial is that the time of arrival of the light signal from the pulsars, they can fluctuate for a number of reasons. But the effect of the gravitational wave has a specific shape as a function of the angle between the pair of pulsar you're looking at. So so if you have n pulsar, you have n times n minus 1 divided by 2 pairs. So for each pair, you consider the correlation of the fluctuation of the time of arrival, and then you get the number as a function of the angle. And then when you plot this correlation as a function of the angle, then it falls somehow spot on, I mean, with some error, on the expectation that you would have theoretically for the correlation as a function of the angle between the pair of pulsar. So this is the smoking gun, because of course you can have spurious correlation, but the fact that the correlation has the exact shape as a function of the angle. And then you repeat that for any frequency. I mean, you can observe over some range of time. So you have a minimum frequency that is given by the total time you observe for, which is order of years. And then you can get to higher frequency, but then of course you lose a little bit of sensitivity, because when you get to higher frequency, you correlate over shorter stretches of time. But what is crucial is the correlation between pulsar at a given angle. that fits the theoretical expectation for the delay induced by a stochastic gravitational wave background. Which is, I mean, if you have some other stochastic source of perturbation, like a density, a scalar gradient of, due to galactic masses or something, would have a different shape as a function of the angle between pulsars.
Right.
But then, so I have a question about integrating this to get the whole contribution to omega.
No, you don't integrate. You look at each frequency bin. You see, this plot is for frequency. So for each frequency bin, you compute what is the equivalent H, the equivalent gravitational wave perturbation, that will give rise to that fluctuation of time of arrival. Okay.
Okay.
So this is omega of f. Omega of f is locally related in frequency space to H. No, omega is just H dot square. So you go to Fourier. So to go to H to omega is just a simple algebraic manipulation.
Okay. So the beam size is typically in nanohertz again, right?
No, the beam size is much yeah, 2 nanohertz, yeah, something like that. Yes.
Thanks.
Great. Now we're learning too also. So this is the interesting part. So the big question here again is we don't specifically know what is the source of this particular signal. So one way to try to elucidate what is the actual source of this signal, we might need to explore maybe higher order fluctuations over this background. So it's possible that, for example, this stochastic background could have fluctuations on it that maybe we are not seeing or we are not able to detect with nanogram. Maybe we will do it in the future. And maybe these fluctuations are the key to disentangle between the difference of astrophysical and cosmological sources. That could be one way. And the idea behind it is that you can have, for example, some gravitational wave signal that depends on the position and the momenta, and then here I will be relating momenta with frequency later on, but it's the same idea. But you can have a background part of the gravitational wave, and then you can have some fluctuations over on top that depends on the position. Similarly, as you have, for example, for the CMB or other background things that we have in the universe.
So that's integrated over all frequencies. This is total.
The total one?
Yeah.
Yes.
It is integrated over all frequencies. So eta, but it is conformal time.
Eta is conformal time, Q is frequency, but then Q is frequency, and this essentially is omega of frequency. So similarly as we saw before, right? And here, for example, these cosmological signals, you see that they span the whole frequency range. They're a function of the frequency.
Why are you using Q for frequency? I got confused.
Yeah, because I will be using it for momentum also. So then I will be transferring from momentum to Q because you can use, yes, in fairness, yeah, should be, we discussed about it. From the computational part, it's easier to keep it in Q, but then for the observational part, it's easier to put it in frequency, then let's choose Q, I guess. For this same definition, you can actually define like a density contrast of these gravitational waves as the fluctuation divided by background. The actual shape of this function here that describes the anisotropies of this background depends on the details of the gravitational wave source. And in practice, as I mentioned before, you can have two sources of a stochastic gravitational wave background. You can have astrophysical sources, which is basically a signal that is coming from supermassive black hole binaries. During its spiral phase, they will produce a background, but then if these supermassive black hole resolve the whole evolution, then this will induce some anisotropies. And since these supermassive black hole binaries live within galaxies, it is said that this density of astrophysical gravitational waves is essentially proportional to the mass distribution because they are correlated with each other. So when we expect a correlation with each other. But for cosmological sources, we don't actually know how this density of gravitational waves for cosmological origin, what is the shape. Because most of these gravitational waves are produced in the early universe. Their initial condition depends on the model that we are trying to use to produce the gravitational waves. So now we'll skip, I will spend like 5 minutes trying to describe what is the shape of this density of cosmological origin. And the idea behind it is that we're going to start by having a population of cosmological gravitational waves and saying that these gravitational waves will be described by a Boltzmann distribution. And this Boltzmann distribution will propagate through the cosmological universe. That is, it will be affected by the Newtonian potential that it travels through. And one can have this Boltzmann equation. And in principle, you can try to expand this the distribution function into a background part and then a perturbation part. And interestingly, I will skip the details, but if you can relate the background part of the distribution function to the background of gravitational waves, and then this gamma function will be encoding the anisotropies of the cosmological gravitational wave background into this system.
So this is a collisionless Boltzmann.
Yes,
right?
yes. Where we consider that the gravitational waves are just
It's the same Boltzmann equation that any
Yes.
even dark matter by these equations.
Yeah, I guess so. If you don't have interaction between the mass particle or whatever. Yes. And then one can try to say, okay, we have the background will if I do this,
That happens.
if I do this still works. Okay. So then we have the background covered by the zero order perturbation, but then the linear perturbation will be telling us about the anisotropies. And once we replace the gamma back into the Boltzmann equation, we have this equation for the evolution of gamma. And the solution of this gamma function essentially has these three components: this one here, this scalar here, and then this integrated effect over the whole universe. I should have delayed this. I didn't have time to correct it, but please ignore that box. And the idea is that the solution of this Boltzmann equation has three contributions. One of them is the initial condition. The second one is an effect that is known as Sachs-Wald effect, which is basically the contribution coming from the initial potential to this Boltzmann distribution, to the anisotropy, basically. And then we have an integrated effect, which is the integrated Sachs-Wald, which is also dependent on the potentials and the derivative, time derivative of the potential. So the anisotropies of the cosmological gravitational wave background have three contributions. Two of them are evaluated at initial times, so at the production of the gravitational waves. And since most of the cosmological gravitational waves are gravitational waves from early universe, this is really early in time. This is really early in time also. But interestingly, this effect is integrated over the whole evolution of the universe. So this effect appears up until today. And then from this gamma, we can relate gamma to the density of the cosmological gravitational wave background via this definition, where n here is basically the field of the gravitational wave background. It's the derivative of the background with respect to the frequency.
So for the initial conditions, you're using something from inflation.
Right. From the initial conditions, I have the freedom to use whatever I want, depending on the model that I want to use for the gravitational wave. And these two effects are independent of the models. These are just propagation. So yes, I will be using inflation models for the issue. So I'm just going to. So as I told you before, the gravitational wave can have like initial condition that could be produced to early universe, and I will be focusing mostly in these gravitational waves known as scalar-induced gravitational waves. These scalar-induced gravitational waves are gravitational waves produced in the early universe due to second-order scalar perturbations. And the idea behind it is that you will have a peak in the power spectrum at really small scales, and this peak will enhance the curvature perturbations, and then these curvature perturbations can be related to gravitational waves in the following way. So under this model, a background gravitational waves is essentially the two-point correlation function of this H, which are the gravitational waves, or the gravitons. But these gravitational waves under this model are related to the two-point correlation function of these zeta functions without the primordial curvature perturbations. implying then that for these particular kinds of gravitational waves, the background of the scalar-induced gravitational waves is proportional to the zeta to the 4, to the primordial coverage of perturbation up to the 4. So
what about the gravitational waves that produce directly?
directly from inflation.
Yeah.
We didn't study those in this particular case.
But they're not relevant.
You can also include them, I think,
Yeah,
but
you can, inflation predicts also those in addition to
right.
the scalar.
But the interesting thing, I think, is that this one are able to produce anisotropies. I think for the primordial gravitational waves is not straightforward how to produce anisotropies. Probably you can have a model to try to interaction between the primordial fields that could produce this. But for this particular case, I will show you later that the initial condition for the gravitational wave anisotropies is depends on primordial motionality, so we have a lot of synergies with the different things. So that is why we select this model in particular.
So all those features that you see
Yes.
in this spectrum is because of non-Gaussianity.
Yes. So here you can see how the background looks for different values of FNL, which is a primordial Marcelli parameter. You can ask me that in detail, but I will not be explaining what is primordial Marcelli. It's just important for early universe and in codes. If you measure it, it's important because it can help you disentangle between models. But in here you can see how the background changes for different values of FNL.
So if FNL is 0, for instance, what happens to this curve?
It still appears. So
Sorry.
it should appear. I think we will have here, but it has to be like a little bit lower. So what FNL does, it enhances a little bit the amplitude of it and produces these weird features here. But yeah, it depends on the details of the values of FNL.
But if it's 0, you don't have these features anymore.
No, if it is 0, I have so it's basically the blue line on top of the red. So in blue, you can see FNL1, in red you have a 0.1. If it is 0, you see just a little bit of that. You don't see much. I should put the FNL 0 in this, but I want to think about it.
And what is, so for FNL equals 0, what is the physical origin of this feature? Thing happening at this case?
You mean the feature in this
Yes.
frequency?
Yes.
The peaks here? Oh, these are produced basically for the mechanism of production of the gravitational waves. So in principle, as I told you before, to produce this background, you need to have something that enhances the zeta to the 4 function correlation. And we usually you can use like a peak in the power spectrum that is a Gaussian, or is a delta peak, or is a log Gaussian.
So you put something by hand.
Right,
In
right.
the scalar perspective.
Yes, yes.
That doesn't come from inflation, something that you put by hand.
Yes, yes, yes. It's a feature that we put in the power spectrum. So for those who don't know about the inflation predicts that you have a power spectrum. P of K, you have K, and it's basically a line, right? The idea behind all these methods of primordial black holes or whatever this scalar induced is that you will produce a peak in the power spectrum that could be produced by models of inflation. We don't know. But the K of this peak is like really small in comparison with the other thing that we see from the CMB. So in principle, we don't see this peak. That's the excuse that people from the early universe can have for these peaks. But they can still be there depending on the modelings. And yeah, so that is why I mentioned also before here that this production of the gravitational waves is also related to primordial black holes, because the production of these waves, this peak, will also generate primordial black holes.
So just to understand, in principle, the FNL is related to non-Gaussian
Yes.
that we will have there. But in the P of K, you are only seeing, I mean, you can have a perfectly Gaussian field if you have only features there. Is that peak at small scales create like second order things that contribute to higher order, like 3.5 or things like that? Like what's the relation between that peak in P of K and FNL?
Right. There is a relation. It's not straightforward, but it depends on the models, right? See, if you have a model that produces peak, a field that has some certain interaction that produces field, then you can compute the triple correlation function of that same field and try to see how the 3-point correlation function will look. And it will definitely not be 0 as the usual case of FNL. So it will have some FNL kind of values, but it's model dependent, right? In here, you can have the freedom to produce these peaks. Yeah, Ricardo? Ricardo? Will answer?
Yes. No, sorry. I thought you were using I thought you were using the standard scalar density perturbation. So you need density perturbation at which scale to feed the gravitational wave at the nanograph scale?
Right, that's a good question. The interesting part of this gravitational wave produced is that you can essentially shift the location of this peak. I don't know if you're seeing the blackboard, but you can shift the location of this peak to try to match a different frequency range for the gravitational wave signal. So for example, in here in this plot is normalized by Q star, and Q star is basically the location in K of this peak.
Okay,
So-
so I just did a back on the envelope computation. You need inverse parsec scale to give a signal at the nanohertz. Am I right?
I don't have the calculation on the top of my head, but I guess so. I
Okay.
guess so.
Okay.
Yeah,
Okay, so
we
you
try to
really
keep our work a little bit more free in the frequency range. So we will not be fixing this omega to the PTA range for reasons that I will explain later. But in principle, we could change the Q to match it to the PTA range, and then try to see how these peaks in which K is located, right?
Okay, sorry,
And
let me
that's something else.
let me rephrase my question. I thought you were using the density perturbation. We already know they are there because they are constrained by CMB, and those were enough to give an imprint. But you're telling me they are not, are they?
Right. No. Because for CMB, I mean, of course, this is for this particular method of gravitational wave production. We could have another cosmological models of gravitational waves, and our results, I'm going to tell you later, but our results is general independent of the model, right? For this case, yes, we will be selecting this particular peak to be in way smaller scales from CMB. So CMB is not able to see it, but it could be still there. And I think that peak located in those ranges, that really small scales, is also within the PDA range. That I'm not 100% sure, but I think I can double check it. But the important thing is that this peak could be moved around, and that will move around the frequency range of the gravitational waves. So in principle, we can move this scalar-induced gravitational wave to any frequency band for each experiment, for example. So we have that freedom in our analysis.
There's something to, for example,
Yeah.
CMB cannot really constrain delta squared, which is the source of this gravitational wave, because it's not sensitive enough. So
Right.
basically, as long as you are below the like second order perturbation theory, you can get very much.
Yeah, basically, yes. That's the idea of this gravitational wave.
Yeah, the answer to Ricardo is not using the delta from the CMB because it needs to be at least an order of magnitude, like a square, a square root smaller than that.
No,
Maybe I
but
missed.
it's a different frequency, but please go on.
Right, okay. So then what is the advantage of these particular gravitational waves, or why we select to use these gravitational waves, is that they have a particular way of induce anisotropies of this pattern. As I mentioned before, the scalar-induced gravitational wave produce a background, and then you can try to look for higher order perturbations. for this particular case of these scalar gravitational waves, the initial contribution for the anisotropies of the gravitational waves depends on this FNL parameter, and it's proportional to FNL times this theta, the primordial curvature perturbations of the long modes. What we're referring to long modes is basically all the thetas that are within this range, right? This one will be a small scales. So when I refer to theta long, it's essentially just the usual theta that we use for CMB or other cosmological analysis. And under this picture, as I mentioned before, the density of cosmological gravitational waves has initial contributions. For these particular gravitational waves, these initial contributions is proportional to an FNL. And you also have the other components, the Sachs-Wolf and the integrated Sachs-Wolf. That's the interesting part, and that's the reason why we choose to work with this particular gravitational wave, because I'm interested in FNL in general, so why not? And once we have the description of the anisotropies, we can use we can summarize the statistic of these fluctuations of these anisotropies by computing the two correlation function, which is essentially the power spectrum of the gravitational waves. And here you can see how the plot of the gravitational wave looks for the power spectrum of the gravitational wave anisotropies from the cosmological wave background look for different values of FNL and for different contributions. So we have, for example, in blue, how the power spectrum of these anisotropies looks for FNL 10. And then in orange, we can see how this anisotropy looks for FNL minus 0.1. And just for reference here, we are also plotting in the dashed lines the contribution from the late integrated Sachs-Wolf effect. So in here, as I mentioned before, this late integrated Sachs-Wolf effect is the distribution of all the three contributions that this has. And the interesting part is that, or as a summary of all the things that I wanted to say from this part, is that the cosmological wave background has three contributions. The initial conditions, which in this particular case depends on FNL. You have and it's proportional to theta, as I mentioned before. So it was FNL times theta, the curvature perturbation. Then we have the Sachs-Wolf contribution, which is proportional to phi, that is the Newtonian potential. And then we have the integrated Sachs-Wolf, which is proportional to the derivative of this phi. These first two are produced at initial times, and then the third one is produced at late enough. It's not produced, it's produced early, but it is appearing over the whole history of the universe.
Sorry,
Yes.
just to understand. So the magnitude of this effect is 10 to the minus 19, 10 to the minus 20. It's just because it's delta squared.
Right. Yes, it's delta gravitational wave squared. It's a small,
But
it's a small
the gravitational wave itself is delta matter squared. Delta
theta
Yeah.
4. Yes.
So the theta is 4. So each one is 10 to the minus 5. So there's 4.
Right. The interesting thing is that all of these things are convoluted with each other. For example, the amplitude of these signals depends on the amplitude of the peak that you put here. The amplitude of the peak here will amplify the signal of the background, and that will affect the amplitude of the signal of these CLs.
Right.
So on and so forth. So it's a little bit model dependent in that sense.
Right.
But in a similar way, all the cosmological models from gravitational waves, as I understand it, will have some dependence of some frequency, some pivot frequency, and some amplitude. And this is the same, right? So the amplitude in here is defined by the amplitude of this peak, and the pivot frequency of the gravitational wave signal will depend in this particular case on where the peak is located. Now,
This late versus, I guess, early split in the integrated Sachs-Wolf effect, like it's achieved range that you are considering, or what's this late against early?
yeah, that's a good question. So, for this particular stochastic gravitational waves, the production of the initial times of the perturbations, it also depends on the location of this peak, which is around for example, I think 1000 or the 1000 for the early universe contributions. The integrated set wall is over the whole retrograde is up until today.
Right. Yeah, so it's like it would also affect in general as an effect to normal like PBH gravitational wave emission. Of course, they would have much less time to be integratable because that I guess the highest ones would be like redshift 6 or something like that. So I don't know. Like my question is this effect also something that would be in the order of astrophysical?
Right. That's a good question. That I don't know. It's a good question. Probably someone already answered it. But in fairness, because if I understand, you are referring to gravitational wave produced by the primordial black holes that could be produced by this mechanism.
No, I mean the integrated such wolf is something that's
Yes.
general. It's just
Yes.
because we have structure formation, we would have some contribution
Yes.
to that.
Yes.
Then the question is, if you have other sources for a background in the gravitational wave, such as from astrophysical sources,
Right.
could this effect be enough to reach a range that is comparable, so it's measurable at some degree? Or
Right. That's the question. That's the question, right? That this is something that we don't know, and this is like probably like first stage to that. I don't know if there is like a complete comparison between gravitational waves, astrophysical and cosmological. And I believe that it's difficult to compare because the cosmological gravitational wave background has so much freedom to produce the gravitational wave. You can select the peak, you can select the amplitude, you can match it to different frequency range. So maybe it's difficult to make like a one-to-one comparison with the astrophysical gravitational waves and try to see whether they are different or not. But this project that I'm showing you today is probably one way to try to differentiate between both of them.
Looking at something, the astrophysical ones are formed already in beacon illumination, and the potentials are constantly illumination. So the contribution to the integration is what is zero.
Right, that's
The only contribution will come from dark energy domination on very large scales, cosmic variance dominated. So I basically say that there should be absolutely no contribution to the physical one that you can detect.
right.
Because it's
So there will be no correlation between them out of the.
I mean, there will be on very large scales where
Right.
much constant is relevant, but again, it's cosmic variance dominated, something that is already noisy. That's not sure if we'll see anything. But for just the physical part. The primordial one is different because it depending on when those are associated, you can go through radiation domination. So it will have different contribution in the one.
Yeah, so that is essentially that will be the freedom that we will try to explore for this project.
Yes, a question in the way in which you compute this as swap and not the integrated one, the actual stuff swap. Because to my understanding, the way you compute usually the swap effect is you go to first order perturbation theory, scalar distribution theory, for I don't know, photon propagation. So you stop at first order. Here you have a quantity, which is the delta GB, that is intrinsically a second order quantity because it's built up from the square of the depth. Right. So
right.
For that scalar induced gravitation wave. So my question is, in order to compute the Sackhole effect, you shouldn't. It seems inconsistent to me to stop at first order perturbation theory.
Right.
Because I expect that this Sackhole effect, so the existence of a scalar field phi, would generate other gravitation waves.
Right. So
more generally, the question: how do you compare the effect?
So for the Sackhole, I take advantage of the difference that I told you before, right? Is that I will be splitting essentially my zeta function, my primordial perturbation, into a long wave contribution and a short wavelength contribution. And I will be neglecting, I will be focusing that, for example, this phi here, the Sackhole contribution is only dependent on it's coming from the long wavelength contribution only.
If you go to the previous slide, like when you do these split things, on the
Yes.
left-hand side, you have something which is second order, right? This is 0 GW, intrinsically in cosmological perturbation theory, because at first order is 0, since there is no coupling with scalar and
Right.
And on the right, you have CL, which is the primordial spectrum. first order, which should not contribute. And I don't know how that cancels out. So unless you're considering only the second order part this CL, it seems to me that you have something that is second order on the left of this equation and something that is first order on the right. So I'm a bit confused by this splitting of the equations in the gravitational equations.
Right. So let me try to see if I can see that. So the production of the gravitational wave is produced as second order, but the anisotropies are linear in theta long. I think that's the difference. So you can produce the gravitational waves by these peaks at small scales, but then the rest of the anisotropies that you have on top of that are for the regular scales. So it's like you produce peaks, and then you have the things that you have on top are from these theta long modes.
So I assume that again, it's not my idea, but I assume that the production of this gravitational wave must stop at some point. Like this, otherwise you would have a feedback on top your first loop.
Right. I think if you have like higher order, then this you're saying that this peak will be producing non-negligible effects over the same.
Yeah, I'm trying to understand like how probably the question is about this specific mechanism of production of gravitational waves that I don't understand fully. Because again, if they are produced by just Galois fluctuations, then I would expect them to be produced also later on from the emergence of other, fluctuations from the matter field.
Right.
But maybe I'm not understanding fully when this happens. So I mean, you can want to discuss.
But the thing is that if you have these kind of peaks, these essentially these peaks are related to very early stuff, right? You will not expect to have it at late universe, right? Because these modes will enter the horizon to generate production at really early times, whether the largest scales will enter to periods that we have now. So maybe that's one reason that you will not have you will not need introduction of that, but I think I have to think a little bit more about that. It is a good question. And I think I have it in paper, but I have to double check. But yeah, that's the main idea. Then, so we have this three contribution from the cosmological wave background. One is proportional to theta, the other one is proportional to this phi, to this Newtonian potential that we have in the late universe, in the early universe of the sun. In contrast, the astrophysical gravitational wave background, as I told you before, are tracers of these delta matter instead. So the relation between delta matter and phi is that you have 1 over k squared factor between the relation between them due to the Boston equation. And this suggests essentially that these two sources might exhibit different behaviors when they are correlated with other structures. Basically, because as I said before, they are correlated with different things. And the cross correlation between gravitational waves and LSS has been explored in the past by a lot of people, including Ricardo, Isabella, from which I stole this beautiful picture. And the idea from astrophysical gravitational wave sources is, as I told you before, it is expected that the black holes live within the galaxies, so then the correlation is expected within each other. And the cross correlation between astrophysical gravitational wave background and galaxies is essentially proportional to this matter power spectrum. The interesting question, or the question that we wanted to answer, is what happens now with this cross correlation if the gravitational wave background is instead of cosmological origin? So I have one LSS summary slide just for you to catch up a little bit with the things that I will be saying after. And for the large scale structure that we will be using, I will be focusing on LSST-like survey, where we have where we will be using the expected galaxy bias values from LSST and the N offset distribution from LSST. And from the galaxy part, the galaxy density is essentially defined by this contribution to the galaxy bias. Then we have a selection function, which is coming from LSST. And then we have the delta matter perturbation. And then just to define some equations that we'll be using later, we can also try to write these in terms of transfer function that is essentially taking all these contributions and putting it in one equation. And then we have the Bessel projection function to compute the CLs. Lastly, I will also include, since the scalar-induced gravitational waves depends also on FNL, I will be including also some primordial longevity in these galaxy bias. And you can see here how the power spectrum of galaxies looks for different values of FNL. So this is the autocorrelation of this delta. You compute the two correlation function of this field, and then you have this power spectrum, the harmonic power spectrum for different values of FNL. That is from the LSS side. So now back to the question that I wanted to answer before is, can we cross-correlate this large-scale structure with the anisotropies of the cosmological gravitational wave background? And as I mentioned before, and I will just keep repeating because this is the important part, we have three contributions. Two of them are at the very early times, and then we have some contribution that is the integrated such wall, which is integrated over the whole history of the universe. And the interesting part is even the two first contributions are generated at really early times, so really high redshifts. It's expected that the cross correlation with galaxies that are around redshift 1 is completely negligible. So these two contributions will not contribute to the cross correlation, but the large-scale structure could be correlated to the cosmological gravitational background via this integrated such wall effect. Interestingly, this has been used before to cross-correlate the cosmic microwave background with LSS directly, because the CMB also have a similar thing as how the anisotropies of the CMB also have a contribution to the propagation of photons through the universe. So this is a similar thing that we have for cosmological gravitational waves, implying that this correlation, if it is also in the cosmological background, it's also connected to the one that we have in the CMB. Of course, at different traces and different objects, but this is one way that we can try to use to see whether this cross correlation exists or not. In here, then you can see that essentially the two correlation function of the cosmological gravitational background and galaxies, the thing that we wanted to compute, is proportional essentially to the power spectrum of the integrated structural effect with galaxies. So then this CL, which is the main result for work, is proportional to the transfer function of the integrated set wall. The transfer function that I showed you before of galaxies that include the galaxy bias, include the set distributions, include all the cosmological cosmological contribution from the LSS. And then we have this integrated set wall transfer function, which depends on the derivative of the growth factor of the potential that we will be using for the integrated set wall effect. One comment here then is that this integrated set wall effect depends on the derivative of the growth factor during the history of the universe. So essentially, this integrated set wall effect has different contributions depending on the time of the universe that we're trying to look for this signal. And as someone mentioned before, in some region, this effect doesn't appear, but then in the transition from radiation domain to matter domain, you also have an effect. And more interestingly, you also have some effect appearing here at almost present times, right? So this implies that this, which is this basically due to the matter domination to lambda dominated transition. This will modify the growth factor, and this will make this effect appear. And here, then you can see how the cross correlation of the gravitational waves, the cosmological gravitational wave anisotropies with galaxies looks for different values of FNL. And interestingly, if you focus your attention in the green line and the orange line, the orange line is the cross correlation of the complete signal of the cosmological gravitational wave background anisotropies cross correlated with LSS. And the green one is when we compute the cross correlation only with the late integrated set wall effect. Essentially, this demonstrates the thing that I told you before in words, that the two initial contributions from the cross correlation will be negligible. And this cross correlation is essentially non-zero and given only by the integrated set wall effect. This is one of the main results that I wanted to share. And the same here again for FNL 10. So if we change the value of FNL, due to the background of the gravitational waves, this cross correlation width rise up a little bit. And then we also have some kind of tilt at these larger scales coming from the scale dependent bias effect of the remote lunar series. So now, as a summary, then
Cosmic variance is huge.
I was going to ask this one.
yes.
But why so much for the larger phase?
So, it's a good question. What is it? What is it? What is it?
When if FNL is large, you have more power in those cases, so it cosmic variance, you also have more variance. But that's the it looks like a huge.
Right. The thing is that the cosmic variance, I would have it around here. So this is why we computed the variance that we put in the plot. And
Yeah.
in this particular, so let me see if I can see this one.
Oh, maybe it's just the way, I mean, the formula.
It is kind of the way it is, but I don't want to say that it is the way it is. I will say the main jump is because of the jumps that we have in the. It's basically this jump that we have here, right? So in here is FNL -1 or -0.1, and this is FNL 10. And this big jump is essentially the transfer back. It transferred to the, okay, this was, oh, okay. So if that jump, this was CL gravitational wave, and this effect will be squared in the variance, right? It will appear here square. So I think it's that jump that is making the things larger to FNL, for the other FNL. Thanks. Yes, project. It was related to the same question.
Yeah.
Okay. So then we have one of the main conclusion for us. It says, as I mentioned before, the astrophysical wave background is essentially a tracer of the matter distribution, implying that this correlation is schematic in this, and this can be computed because it's essentially a matter power vector, and is proportional to 1/L+1. And interestingly for us, since this cross correlation is now given by the integrated Sagwell effect, and the integrated Sagwell effect traces the internal potential instead of the matter distribution, the dependence on the CLs is different, right? So this correlation with the cosmological and galaxies looks essentially like this. This quick approximation that we did, and it looks like 1/√² of this. And this implies then one of the big results that we found is that this cross correlation can actually be used to distinguish between one of each other. So we might not know what is the source of the gravitational signal, but if we compute the cross correlation with large structure, they must behave in some way depending on the source, right? Maybe some scales, maybe it's a mix, we don't know. The interesting part is this actually is a contribution. This is one would expect that maybe this contribution was 0 to begin with. But this essentially tells us that galaxies could also be correlated to the cosmological part of the gravitational, implying that this correlation now should be taken into account into analysis of the cross correlation with stochastic gravitational background and subgroup gravitational. The stretch is a little bit, but it is our subgroup. Yes, this is the main result. Both of them are different. We can distinguish them. How much time do I have left? 2 minutes. Now, the interesting and difficult part of this analysis was trying to see whether this cross correlation signal can be detectable. Detectable in a sense of, first of all, can survive can be detectable under its own cosmic variance. And second, could be detectable from some future experiment from the gravitational wave part. And in here, from our work, we also performed like a quick SNR analysis, trying to study how the signal to noise ratio behaves in comparison with this cross correlation compares again its variance. where the variance is defined by this. So in here you have the contribution of the CL from galaxies. In here you may notice that I'm ignoring shot noise from galaxies. This is mostly because we will be focusing on the large scales. And then we have the contribution from the gravitational waves, and then we have the noise of the anisotropies of the gravitational waves. And those are mainly our ingredients here. We also will be computing, we'll be considering that we have an idealized full sky scenario, implying that this F sky is 1, so we will just complete the full correlation. And in here, just to have some idea of which experiment we will be using, you can see here how the noise of the gravitational wave changes for different gravitational wave experiments. Again, this is the noise in the anisotropies that they will be able to detect. And in here in the dots, you have Lisa with the crosses. In the dash, you have Einstein telescope, cosmic explorer combined. And then in the dash dot, you have the LK, so LIGO, Virgo, Gaia. Interestingly enough, in here you can see from this noise, you can see that the Einstein telescope combined with Cosmic Explorer has a better sensitivity to a larger number of multiples. Which essentially, this is also one interesting thing, is that this is also a really large scale. So the multiples that the level of anisotropies that the gravitational wave detectors are able to detect is a really large scale. That's one thing that I want to mention. But also the ET plus CE has a well one detectability. So this is the one that we're using for our SNR analysis.
Why Lisa gets so bad that L is larger than because they're
That I'm not 100% sure, but I imagine that
too large.
it will sacrifice the resolution, the high sensitivity in the monopole, but then the multiple is really more difficult to detect because maybe it's moving around. I'm not sure. But interestingly enough, as I told you before, our model or this cross-correlation analysis can be essentially moved around to match all the frequencies the pivot frequency of each experiment, right? So in principle, we're gonna try to see how things look for Lisa. We're gonna try to move it to LDK. We're gonna try to move it to PTA. The big question like here is that all people question me when I present this, it was that why not apply directly to PTA? You started your talk mentioning PTA and everything in PTA, and I will not be applying it to PTA at the end. And the short answer is that I didn't know how to compute this for PTA. But apparently there is people that know how to do it. So I didn't have no idea at the time how to do it. So we just decided to have one with a good enough sensitivity for the multiple. And then with that, we compute the error.
Just something I don't know. This noise is for different L's, but is it frequency dependent as well?
Yes, it depends on the pivot frequency of the whole experiment.
So this is for a given frequency.
Yes. Yeah, all this analysis is essentially given for a given frequency, right? At some point I have to fix at which K I'm putting this peak, which will be related to the frequency, to the range of frequency of the background gravitational wave signal is located. And then that will be related to the frequency at which the noise is computed.
And they're thinking of nanohertz usually, right? That's the frequency you're thinking about.
That's the thing that's the disclaimer that I'm telling you now. And now I'm moving to the other range, right? I'm not back to PTA range. I'm moving to the ET-CE LIGO range.
So you're using the signal, let's say the smoking gun from PTA.
Yes.
To predict something that can be seen at other frequencies. Is that the idea? No.
That should be the idea, but I didn't know how to compute the noise for the PA. We just, at the end, in a more personal way, we just wanted to shift a little bit gears of the idea of the project, right? Because if we mention and we focus only on PTA, then you might get confused that this effect will appear only on PTA. But in principle, this correlation and the way how it produces and how they produce anisotropies is completely independent on the frequency, right? We can select any frequency range, try to match it with any gravitational wave detector, if we have some access to the noise. And then this correlation will still exist. So that is why we didn't want to restrain ourselves only to the PTA range and say, okay, we will be focusing on PTA. Because it could be applied to other cases, right? That was a little bit our personal discussion. But then with this definition of the SNR, we compute the SNR for these models. So I'm showing you here the whole SNR plot and we'll give it to you what you consider detectable or not. One thing that I can tell you is that the SNR, in here in blue, you see how the SNR looks when I consider only cosmic variance, that is neglecting basically this and GW. And in orange, you see how it changes when I consider the noise of the detector. One interesting thing that you can see here is this, the SNR of this cross correlation within the scalar induced gravitational wave analysis is highly dependent on the primordial nova affinity parameter, that is on FNL. So that was one of the reasons that we wanted to do, right? Because it seems that this primordial nova affinity parameter that affects also galaxies and scalar induced gravitational waves, they could have synergies within each other. And maybe that could help us to improve the signal to noise ratio of these particular signals. And that's actually what we're seeing here, right? You have this big peak around FNL minus 0.1. Whether that's detectable or not, we'll leave it to you again. Well, also, obviously, this signal to noise ratio gets worsened as we include the gravitational wave detector noise. And that's one of the main conclusions, right? We have in the green line and the red line is what if we use instead other sources of cosmological gravitational wave background. In this particular, I think we use some phase transition model that doesn't have much contribution to the initial contribution of the Anisotropies, but it has a such wall and integrates as well. So that is why we refer here to FNL, to FNL gravitational wave 0. And you can see also that in here, the scalar induced gravitational waves has still better signal to noise ratio in comparison with a more general gravitational wave. So this was one of the main results. So
why minus 0.1 as a peak and not 10? Okay.
Right. The answer to this why question is again similar to the why the cosmic variance
Comes out like that?
It comes out like that, but I believe
There
it's
must be a reason.
yes. Our understanding is because of these. No. So that's why I will be showing you here 10 minus 0.1, right? One interesting thing that happens at minus 0.1 is that the autocorrelation of the cosmological gravitational waves at large scales, you can see it essentially matches the contribution from the late integrated circle. So for this value of FNL, at these scales, the signal is essentially dominated by the integrated circle effect. So I believe that could be the reason, right? So in here, on this value, is like you are basically saying that your cross correlation is coming from the integrated circle effect, but also your gravitational wave signal is purely integrated circle effect, right? And I believe it's this contribution of both of them that is making this peak up here, right? For this particular value.
Okay.
Yeah.
Go back to your expression for the covariance.
Yes. Variance.
The one with
I'm ignoring covariance.
so the one with the cosmic variance that you have the contribution from galaxies and one from FNL. There was like some sum with L once per root of. I think it's one line to like. Yes, this one, sir.
Yes.
Yes,
Right.
I mean, it seems to me that this FNL minus 0.1 is kind of the generic, we could say, the outcome of the scope.
Yes, it would be. So maybe I'm writing it wrong, right? This A is essentially a not that free parameter. It includes all the contributions coming from the scale dependent bias, basically. I just put A to simplify the expression, but it's not a a free parameter in our theory, right? There could be the generalities with other cosmological sources. So for example, A encompasses all these B, this omega m, this H naught, this B minus P. Basically, all these things in a regular galaxy analysis, they are all of them also degenerate with FNL. So they could be there are degeneracies with FNL hidden in that A. So yes. But the good thing is that all those degeneracies are kind of studied for the galaxies analysis. So one would expect that these degeneracies, the degeneracies from A and FNL could be under control under a regular MCMC analysis for try to measure this. But there's also, this is an analytical approximation that we have under some assumptions. So essentially the behavior that we see here is the behavior presented at these, up to this scale, because then over here we have to model the transfer function, but the approximation is just to make just to start the large scales, which are interesting parts also for the considering the noise. So, but for the SNR analysis, we are using the full computation factory. But yeah. So with that, I'm finishing my talk. So I have one last slide, is that maybe this cross correlation, we include FNL on the whole thing. So maybe why not try to put some forecasts on FNL by using this cross correlation. And the idea was really simple. We will consider a feature information matrix, ignoring covariance, of course, just a simplified case. And the error that we could obtain from this cross correlation will be defined as this, right? The root square, the 1 over the root square of the Fisher information matrix, just to have a quick forecast. And here you can have, for a model, we're using different fiducial values of FNL, all of them kind of close to 0. And we will be comparing how the important variable is this column here, which is the constraints that we could obtain from LSS and the cross correlation. And we have, for example, an FNL that we can have a sigma FNL around 10 or 11. And this can also be combined to the LSS one in a multi-trace kind of spirit. And you can see that, for example, if the errors of LSS are around this value, then the combined can help us to have an improvement of around 4-5% of improvement by including this cross correlation. But I do consider that this is a little bit of a stretch, so, but it was interesting, it was there, so why not to do? And that was my talk. That's the thing that I wanted to say. The main summary, the cross correlation between galaxies and the cosmological background is actually non-zero. This was the result represented. It was driven by this integrated circle effect. And the interesting part is the cross correlation behaves differently if the cross correlation is coming from the cosmological origin or is coming from an astrophysical one. So maybe this is a potential now a new thing that we want to try to do, try to differentiate more in detail. Or maybe like maybe in the future. And also is that the scalar-induced gravitational waves with the scale-dependent bias has a better detection prospect than other cosmological gravitational wave background, maybe due to the synergies with Primordial Negocianti. And as I told you before, you can use this cross correlation to try to measure FNL. And maybe even combine it with logical structures. So that's it. Thank you.
For questions or Paulo?
The paper is there if you want to read it. It has a couple of weeks. We still haven't sent it anywhere. So if you want to read it and make us comments.
Comments?
I have a question. Certain slide have shown the distribution function, like the background one. And my question is if you assume a distribution function or if you calculate this.
The distribution function of
The background one in the very beginning of the draw.
so maybe around here.
Here, yeah, this F bar, you assume this or you calculate from a theory.
Right. In principle, you assume that you have any distribution function that it depends on the position and the momentum. And then you compute the Boltzmann equation. But then the interesting part is that I essentially this distribution function to be related to the gravitational wave that I'm trying to look for. So for example, as I said before, if I expand this distribution function up to this point, I don't know what it is. It's just a function. I'm just doing an expansion over a background and the position. But then I will be relating that this background is related to the gravitational wave, right? So in here is where I connected to the usual gravitational. But up to this point, it's just a distribution function. I'm not really sure the statistical properties, but it has to be Gaussian at this point. I think up to this point, you have complete freedom on this distribution.
Okay.
And then it will relate to the other thing. Yeah, good question. I have to think about it.
Probably Bose-Einstein.
You have to be able to, they have to have some statistics, right? You cannot be,
Bose-Einstein's like
yeah.
Bose.
yeah. All right, yeah.
So let's thank Walter again. We'll have a break. Let's